Okay, so this is our video lecture for lecture 7. We're going to go ahead and talk about the Doppler effect. The Doppler effect is seen in our daily lives in a few different instances. One common instance is, let's say, you are somewhere on the street and an ambulance drives by you. So let's say you're standing here on the sidewalk, there's an ambulance, it's siren on, it approaches you, and then it goes away from you. When it's approaching you, the frequency of the siren that you hear is different than when the ambulance is going away from you. Next time you're out and about driving or walking around, try to take a note of that frequency. And I'll also bring a demo in class on Thursday to try to show this effect. So Doppler effect can be summarized by looking at the following. So let's say you have a source that is moving to the right, and let's say you're standing here and listening to the sound wave. So let's say the source is outputting some kind of a sound wave. So what's happening is the source has these crests or these wave fronts that are being emitted, but because the physical source is moving this way, the wave fronts get bunched up on the right side here, and then the wave fronts get spread out behind the source as the source moves to the right. The overall effect is the following. The wavelength of the wave behind the source compared to the wavelength in front of the source is different. So in front of the source, you get a shorter wavelength, and behind the source here, you get a longer wavelength. So let's see what effect that has on frequency. We know V equals lambda times the frequency. This is the wave velocity. This depends on the medium, so that's not changing. If wavelength goes down, which is in front of the source here, we know that the frequency as a result must go up. So the perceived frequency heard by this person here is louder, or sorry, not louder, my apologies, is higher than the frequency of the source itself at rest. So when you're on this side, you hear a higher frequency. And then behind the source, as the source is going away from you, because, so V equals lambda F, because the wavelength is longer, because these wave fronts are getting spread out, the frequency would be lower. So you hear a lower frequency on this side. So let's try some examples of this. And again, we're not doing these as clicker questions, these are concept checks. What I encourage you to do is pause the video, answer both this question and the next one, and then you can take a look at the answers in the video. So in this case, we have an ambulance with its siren on that's driving towards you while you're standing on the sidewalk. How does the frequency of the sound perceived by you compare to the actual frequency of the siren? So when the siren is, let's say here's the truck at rest, when the siren, let's say here's the siren, sounds, it outputs, the wave fronts are, so what I'm trying to draw is equally spaced wave fronts starting at the source here. Now, if we let the truck move towards us, so let's say we're standing on the sidewalk over here, and now the truck is moving to the left. Well, when the truck's moving to the left, what happens is that the wave fronts start bunching up in front and start spreading out in the back. So basically, shorter wavelength on this side, you end up hearing a higher frequency of the siren. So the sound perceived by you is at a higher frequency than the actual frequency of the siren, which would be the frequency of the siren at rest. And then this next question says, now let's say the ambulance is parked with its siren on, and you just passed by the ambulance, and now, this should be a W, sorry, and now you are driving away. How does the frequency of the sound perceived by you compare? So same deal again. The ambulance is parked here, and it outputs wave fronts that are equally spaced because it's not moving. But the fact that you are walking this way and going away from the source, basically the perceived wave fronts that you receive become spread out. And if they become spread out, then you basically hear a lower frequency sound. So you going away from the ambulance is similar to you standing still, but the ambulance going away from you. It's essentially just how are the two, you and the truck, moving relative to each other. So in this case, you end up hearing a lower frequency than the actual frequency of the siren. So let's try to summarize this in an expression. What if we want to quantify how much lower or how much higher the frequency is? This is what the Doppler frequency shift formula tells us. So here, there's a few variables we need to keep track of. So if the sound source is moving with Vs and the observer is moving with V0, the Doppler shifted frequency is this formula here. So in this formula, V, without any subscripts, is the wave speed. Vs is the source speed. Oops. And VO is the observer speed. And how do you figure out what's positive, what's negative? That's what this bullet point here tells you. Pretty much, you should plug in positive numbers for V source and V0 if the source and observer are moving towards each other. And you should plug in negative numbers if the source or the observer are moving away from each other. And we'll see this in examples to keep track of this. So here's a practice problem. You're standing still while a train runs by at a speed of 50 meters per second, blowing its whistle. What is the percentage difference in the frequency you hear after the train passed you compared to when it's approaching you? So we want to do a case of approaching and basically pass after it's passed by you, so going away, approaching versus going away from you. So for each case, let's start by just writing down our Doppler shift formula, and then we can ask ourselves what the signs of everything is. So F prime equals V plus V observer divided by V minus V source times F. Also, one thing I didn't note here in this formula is what is this F? This is just the frequency, the frequency of the source when nobody is moving. So this is the frequency that's being output, and this is the frequency that's being heard by the observer. So the frequency of the train whistle, that's F. This is what we're perceiving when it's approaching us. So when a train is approaching you, is the observer moving or source? Well, you're the observer, you're standing there, so that's 0. This is the train speed. Now we ask ourselves, should we plug in Vs as a positive or negative value? Well, since it's approaching, we plug in Vs as positive. So here, V source will be positive 50 meters per second. V is the speed of the wave. That's 343 meters per second. The speed of sound in the atmosphere, given that the temperature isn't significantly different than room temperature. So that would be the approaching case, and we identified that V observer is just 0 because you as the observer are not moving. Then F prime as it's going away is going to be V plus V observer over V minus V source. Now in this case, you're still at rest, but now the source is moving away from you. So when the source is moving away from you, then we plug in V source as negative 50 meters per second, V as 343 meters per second, and then you as the observer are still at rest. So what I'd like you to do is plug in these numbers and see what fraction you get. And for this case here, the number you get for observing is that the frequency you hear is 1.17, approximately 1.17 times the frequency of the train, and then in this case you'll get that the frequency is about 0.87 times the frequency. And now if we compare them both and calculate the percent difference, so percent difference is new minus old over old times 100. So we're comparing the percentage difference you hear when the train has passed compared to when it was approaching. So 0.87 in comparison to 0.17. And when you plug these numbers in, you should get that this difference is approximately negative 25%, meaning there's a decrease in frequency, which makes sense because when the train's approaching you, you hear a higher frequency. When the train's moving away from you, you hear a lower frequency. Alrighty, here's our practice problem number 2. This problem is a little bit more complex and challenging, so we're going to break it down into pieces. We have a stationary bat emits a chirp. The sound bounces back to it off a moving moth. Its ears detect the return sound frequency is 5% higher than the emitted sound. How fast is the moth moving towards or away from the bat? Here's a picture of what's happening. We have a bat. Also, this bat is stationary. So bat's not moving. Let's just say bat's hanging off a tree or something. It emits a sound wave. Then there's a moving moth. The moth could be moving towards or away from the bat, and then reflects the sound, and then that reflected sound is then heard by the bat with a frequency of that's 5% higher than the frequency that the bat is emitting. And we're being asked to find how fast the moth is moving in which direction. Well, the fact that, so here's a more basic picture. Bat is here at rest, and then we have a moth here, could be moving to the right or left. Well, if there's a sound wave coming from the bat to the moth, and then getting reflected and heard at a frequency that's higher, we know that the source and the observer have to be approaching each other. And the thing that's moving here is the moth, so the moth has to be approaching the bat in order to result in a higher frequency. So that's the first part we can answer, that it's actually moving towards. Then we break the problem into 2 steps. The first step is the moth is observing and the bat is the source, because the bat outputs some sound wave and the moth is like the observer. So what frequency is the moth seeing? Well, since the moth is moving towards the bat, in this equation we have velocity of the observer and velocity of the source. The velocity of the observer is going to be the velocity of the moth, and it's going to be a positive value because they're approaching each other. And then the velocity of the source is 0 because our bat is stationary given in the problem. So the frequency that the moth observes is the following expression times the chirp frequency that the bat had originally emitted. So the moth hears the following frequency. Now step 2 of the problem is the moth is now the source, because what happens is the sound wave that arrives here gets reflected in the opposite direction, and whatever sound wave that the moth is receiving, that's the same frequency that's getting. So in the reflection, there's no change in frequency. In the receiving frequency, there's this shift, but then as that sound wave gets reflected, there's no change in frequency. Basically, it reflects at this same frequency. So now the moth is outputting a sound wave at this frequency, and we want to know, because the moth is moving towards the bat, how that gets shifted. So now step 2, moth is the source, bat is the observer. In this case, the source is now moving because the moth acts as the source, and the source is moving with v sub m because that's the moth. And now bat, which is the observer, is no longer moving, so we plug in 0 for the observer. And the frequency that we plug in here is the frequency we just solved for. So basically, we're going to take this, let's use a different color. We're going to use this part of the expression here and replace it with this whole thing. So this is what we plug in for fmoth. So let's take a look, see if we agree. V plus Vm over V times F church, and that's exactly what we've plugged in here. Now we put everything together. What the bat hears and receives back is the product of these 2 quantities times the original chirp frequency. Notice the factor of V on top and bottom here cancels out. And if we multiply these 2 fractions, we basically get V plus Vm on top and V minus Vm on the bottom times F chirp. Then what I've done is I've gone ahead and divided both sides by F chirp, divided both sides by F chirp, because that's what's given to us. The ratio between what the bat hears versus what the bat has chirped out, that is
5% higher. Pretty much what the bat is receiving is 5% higher. And the way we show 5% higher is just 1 plus 0.05, and that gives us 1.05. Basically, if something's 5% higher than its original value, it gets multiplied by 1.05. And that is all equal to the following fraction here. In this fraction, for v, we plug in 343 because that's the speed of the wave that's propagating. It's a sound wave. And vm is what we want to solve for. So in this equation, after you plug in 343 and solve for the velocity that the moth is moving with, you should get about 8.4 meters per second. Now this is a fairly challenging and involved example. What I'd encourage you to do is pause the video and see if you can go through the reasoning yourself. Okay, now we're going to start reviewing some things from last week. We had talked about the concept of wavefronts. A wavefront is a curve that connects points of constant phase. So in 2D, let's say you have water waves that are moving in a pond. Well, you can track all the crests and see when they move across. Basically, our wavefronts look like straight lines, and the direction of propagation is this way. On the other hand, let's say you have a point source. Let's say you have a pebble that's making disturbances in a pond of water. There, the wavefronts are circular, and they propagate outward. And in that case, our direction of propagation are these arrows that are perpendicular to our wavefront. So in 2D, your wavefronts can look like lines propagating outward or as circles propagating outward. When we go to 3D, basically things can become planar. So you can have spherical shells, or you can have planes of constant phase that propagate outward. And we'll talk more about that in a future lecture. The reason why I remind you of this is the understanding of wavefronts is important for Huygens principle. So as we talk about how waves interfere, how they interact, we need to be familiar with the ideas of wavefronts, with the ideas of propagation, and then finally with Huygens principle. So what Huygens principle says is that every point along a particular wavefront behaves as a new source of small spherical wavelets. As the wavelets propagate out, their envelope defines the new wavefront. So let's try to break down what this means. So here's a source, and let's say it has circular wavefronts. It's a point source. This is what the wavefronts look like. Let's consider one of the wavefronts, for example. What Huygens principle says is that every point on this wavefront can be thought of as a small source of spherical wavelets. So this point can be a source where you have wavelets going outward. This point can be a source where you have wavelets going outwards. This point can be a source where you have wavelets going outward. So let's say we superimpose a bunch of these. So here's some more points, some more points. What's happening here? If we try to now track the boundaries or the points of constant phase, what you'll see is you still end up with spherical wavefronts propagating outward. So you can think about the original set of wavefronts as being the result of every point on this wavefront being a tiny little source. So if this idea is a little bit confusing, we're going to continue talking about it and revisiting it, so you'll have a chance to ask questions. So the reason for talking about Huygens principle in this lecture is for us to look at the idea of reflections first. So let's take a look at the simulation that I have here of what happens when you have a wave that's incident at a boundary, and we'll take a look at reflections. Let's go ahead and start the simulation. As the wavefront comes in, you'll see that each of these pink points are now acting as tiny little wave sources. I'm going to pause it here. The thing I want you to pay attention to is the blue part is the reflected wavefronts, and then the red part is the transmitted wavefronts. Let's just focus on the blue wavefronts and go back here. So if we pick the points of constant phase from the blue wavefront, you'll notice that if we connect the points of constant phase from the blue wavefront, we get a line that looks like this. If you compare with respect to the vertical, if you compare the angle of the incident versus the reflection, you'll see that both of these angles are the same. Now we have to be careful. This here is where the wave fronts basically are traveling, and this is where the reflected wave fronts are going to be traveling. The reason why I say it's to be careful is these angles are usually defined for the ray diagram. So if our wave fronts look like this, just a reminder from before, rays are perpendicular to our wavefront. So really the rays from the incident wave looks like this, and then the rays from the reflected wave are going to look like this because it's reflected off the boundary. But the first thing we're showing here is that when you get reflections off of any kind of a medium, the angle of reflection is equal to the angle of incidence. Now let's look at the difference between medium 1 and medium 2. So we revisit the simulation. If you'll notice closely, the blue wavefronts are getting further in the same time that the red wavefronts are not getting as far. So the wave propagates faster in the yellow part and slower in the blue part. Well, what does that tell us about the transmitted part? So similarly, what we're going to try to do is now draw wavefronts tracking, is try to track points of constant phase in the blue part of the medium. So now I'm going to go to just redrawing that picture, and I've drawn a bunch of lines here. What do these lines represent? So all of these blue lines that I'm highlighting in red, these are the wavefronts for the incident wave. And then these red lines that I'm highlighting are the wavefronts of the what we call the refracted wave or transmitted wave. So the refracted / transmitted wave. So pretty much whatever gets through, that's transmitted. But the fact that what is transmitted is bent at a different angle than the incident, that's the whole idea of refraction. That's what we call refraction. And that's why I'm calling it the refracted wave. So what's happening to the angle of propagation? This angle of propagation with respect to the incident is bigger. And this angle of propagation with respect to the incident is smaller. So we know that this here is the faster medium, this here is the slower medium. So in the faster medium, we have a larger angle with respect to the vertical of propagation, and then when it reaches the slower medium, we have a narrower angle with respect to the perpendicular. So you can use this simulation and the results we're seeing from here to say how a wave might go from one medium to another and how the transmission might change. And finally, the bending of the wave that we're seeing here, this is exactly what is refraction. So refraction of a wave, the analogy that you can use to come up with the same result that we just saw here is you can think about a toy car. So think about having a toy car that is on some smooth ground. So let's say you are in your kitchen where the floors are tile floors. Okay, so the car is moving pretty smoothly and fast on the tile floors. Let's say you come to the boundary of entering your living room where there's carpet on the floor, where the car slows down. If the car is coming in at an angle where this wheel catches first compared to this wheel, notice that this car is going to turn towards the normal line because the outer wheel, which is on the plane floor or the tile floor, is going to travel faster than the wheel that's now on the rug. So when you're going into a slower medium, you can see how this toy car would turn towards the normal line. That's pretty much an easy analogy to think about wave propagation. When you go from a fast medium to a slow medium, what you'll see is that, so let's draw the two perpendicular lines. So here's my line that's perpendicular, okay? And then in the slower medium, here's my line that's perpendicular. If I compare the two, pretty much draw them, I draw them in the same location. So if I redraw that red ray here, it's going to look something like this. And then the black ray, we can see looks like this. With respect to this perpendicular line, this angle theta 2 is smaller than this angle theta 1. So theta of the ray that's propagating gets smaller with respect to the line perpendicular in a slower medium. Okay, so using this knowledge, let's see if you all can answer this next question. What can you tell from the picture about the wave that's passing from medium 1 to medium 2? And I want you to pause the video and I want you to think through the two angles. So here's theta 1 and here's theta 2. Okay, hopefully what you came up with is the fact that the wave is traveling faster in, let's think. So I have to think each time of the toy car to help me make sense of this. So I have a toy car, here it is. So what I'm noticing right now is, since it's bending away from the line that's normal, this wheel is going faster than this wheel. Well, the wheel that's going into the medium 2, if it's going faster to turn this way, we must be going into a faster medium. So the velocity in medium 2 is greater than the velocity in medium 1. Okay, here's another one. So think through, now that you know that the velocity in medium 2 is greater than velocity in medium 1, what can you say about the wavelength? So again, pause the video and think about what you might say about the wavelength. Okay, hopefully you paused the video and thought about it. So let's take a look at V equals lambda F. We know V2 is bigger than V1. So let's see how lambda compares. So lambda is equal to V divided by F. And we know F is set by the source, and the source isn't changing. So lambda and V have a direct relationship, meaning if V2 is bigger, then lambda 2 must also be bigger according to according to our wave equation, because frequency is staying fixed. You have some kind of source here that's outputting these waves, and that same source is then the waves from that source are being transmitted in medium 2. So the frequency is staying fixed, and the wave velocity and the wavelength have a direct correlation. Okay, the last part of this lecture video is talking about diffraction. We'll actually pick this up in class on Thursday.